friction, so what's the word static mean? Still or at rest. So static friction means it's the friction when things are at rest. Okay? So friction when things are at rest. And specifically at rest with respect to the surface that they're touching. Okay? So at rest with respect, there's a light missing. Is that light missing? Friction when things are at rest with respect to a surface. This sounds a little bit silly, but for example, this book is at rest with respect to the table, and if I push the table, the book is still at rest with respect to the table as I push things along. So the friction associated with the book is actually a static friction, even though the whole table is moving, because the book is at rest with respect to the table. Okay? So be careful with that. Things can move and have static friction if the surface they're touching is moving in the same way. Okay? Okay, so this friction keeps things from slipping. So you know that if you come to push something, so like I'm going to come push the table, right? And I'm pushing on it a little bit, and it's not moving. So something is hindering that push. If we were on a purely frictionless surface, if I barely touched that thing, it would just fly across the room. Not necessarily super fast, but it would definitely move. So I come up and I barely touch this, and it doesn't move. So there's friction opposing that. I push a little bit harder, it starts moving. Push a little bit harder, still doesn't move. Push a little bit harder, still doesn't move. At some point, I push hard enough that I break the friction, and then it'll actually start moving. All right? So if we think about like a box, where I'm pushing, let's say I push with 1 Newton of force. There is friction, and the box is not moving. But I'm pushing on it. So here I am, I'm pushing on this object, it's not moving. What must the opposing force be if it's not moving? It's got to be 1 Newton. Does everybody get that? If I'm pushing with 1 and this thing is not moving, it's got to be 1 Newton. So there's some frictional force. We designate friction with a lowercase f for some reason. I don't know why this is, it's kind of weird. We do uppercase f's for almost every other force, but for friction it's a lowercase f. And then there's this little subscript s for this static friction, right? So static friction is written like that. I can go through and be real formal about this, and I can use what you guys have learned about F equals MA, and I can go through and think about that in terms of this. I can think, okay, in the x direction versus the y direction, and all professors kind of think about this a little differently, so I'm sure what I'm writing up here is slightly different, but it's the same idea. Does Dr. Houston talk about this? Does he use this sum of forces notation?
Yeah.
Yeah? Okay. Or you can think about it, I mean, we know that F net equals MA, right? We know that's Newton's second law. So we know that's true. So that's true in the x direction. So I'm just going to put little subscripts x's on everything. It's also true in the y direction, but I'm just interested in the x right now. So the net force in this case, I've got 2 forces. So if I define the net force, I've got to add up my 2 forces. I've got a 1 Newton that points that way. And I've got this static frictional force that points to the left. So I got to put a little negative sign on the static friction because it points to the left, right? So I've got the 1 Newton to the right, it's positive. The frictional force to the left is negative. It has to equal mass times acceleration based on Newton's second law, but it's not moving. So what's its acceleration? 0. Since it's not moving. And lo and behold, in my formal way, I find that the static friction is also 1 Newton. So I don't know, sometimes sometimes, like I make my students be more formal, some professors don't make you do that. If I had a student that just told me static friction equals 1 Newton, I wouldn't want to know why. Either from a mathematical sense explain to me why, or say, well, it's not accelerating, there's only 2 forces, they have to balance each other, friction has to be 1, okay? So I have this box, or this table, pushing on it 1 Newton, it's not moving, the frictional force has to be the exact same value as the push force. So let's push a little harder. I'm going to push harder, but it's still not moving. And I'm going to push now with 5 newtons of force. There's still static friction, and we could go through the same argument and say, okay, obviously the static friction is now 5 newtons. Because it's not moving. So static friction is a very weird thing because it changes its value based on your pushing, and that is really weird. Right now, the static friction on that table, between the table and the floor, is 0 because nobody's pushing on it. If it were something more than 0, it would be moving it. So right now the static friction is 0. Now the static friction is 1. Now the static friction is 2. Now the static friction is 3. Now I start to move it, static friction doesn't even exist anymore. So it's this very weird property. It's actually based on the bonding that's occurring between the atoms. And this is a physicist talking. This is not a covalent bond or an ionic bond. If you're a chemist, it's not that sort of bond, okay? But there is an attraction between the floor and the desk, the wheels of the desk. It hasn't formed covalent bonds or ionic bonds yet. But nonetheless, there is still a force of attraction between the two. And it's similar, it's not a chemical bond, but some sort of force of attraction. And when we push on the desk, we're breaking that, right? We're having to rip the wheels of the desk that are sitting on the floor, we're having to rip them away from the floor. And it's not like a covalent bond where it's really a strong bond, it's a really, really weak bond. But this is what friction is. And it's not something that chemists ever talk about. You will never hear chemists talk about that sort of bond. You only hear physics talk about it. So if I say the word bond in front of a chemist, they like immediately go to hydrogen bonds or ionic bonds or covalent bonds, and that's not what I'm talking about. Okay? So I'm just saying there's a force of attraction between the two. And this is what friction is. And so what happens is as I push and I push and I push, right, I'm kind of stretching that force between the two and stretching that connection between the two, and eventually I literally break that connection. Again, not like I would have to break the connection of the covalent bond in this desk by sawing it in half, right? It's not nearly that strong. So I push, the frictional force is small, I push larger, the frictional force is bigger. So we can write this mathematically this way, that the frictional force is less than or equal to some maximum force, right? At some point, the static friction becomes some maximum value, and at that point, the desk moves. So when static friction reaches its max, the desk moves, and there's no longer static friction. It ceases to exist. A new friction comes into play, which is kinetic friction. It's really the same physical phenomenon, but it's a different value. All right? So we think about it as two separate things. So when static friction reaches its max, the object moves and there's no longer static friction. So I start with 0 on this desk, 0 static friction. I push on it a little bit, I get 1 newton of static friction, 2 newtons of static friction, 3 newtons of static friction. Now it starts to move. 3 was the max. And so the static friction in that case varies between 0 and 3. That's what the less than or equal to means, right? Between 0 and 3. It has to be bigger than 0, but between 0 and 3. So there are a lot of problems in your books that will say something like, it'll say stuff like, the instant the box begins to move, or the instant before the box begins to move. If you see that, instant before box moves, or it'll say the maximum force that you can push on it without it moving, right? And they usually give you words like this to indicate that the static friction is at its max. So static friction is particularly strange because of this idea that it changes values based on what I'm doing. Now, you guys know if you've ever moved something heavy, if you've ever tried to slide like a heavy dresser across the floor or anything like that, that it's harder to get something moving than it is to keep it moving. And that is because there's a new friction that takes over when the thing starts to move, and that new friction is actually smaller than the maximum static friction. So if there's something really heavy, you know, it's really hard to get it moving, it's easier to keep it moving. Think about if you've ever had to roll a car that's dead. Getting the car to start rolling is really hard. But then once it's rolling, it's okay. It's not as bad to keep it going. So there's a new friction then. That once the object starts to move, kinetic friction takes over. And this is the friction of motion. Static friction is the friction when things are at rest with respect to the thing that they're touching. Kinetic friction is when they're in motion with respect to the thing that they're touching. Okay? So friction of motion, if object moves with respect to thing it touches. So desk example, actually let's not do this. Okay, calculator on the box, right? I'm pushing the box. The box is experiencing a kinetic friction between itself and the table, right? Kinetic between the box and the table. But there's a static friction between the calculator and the box because they're not moving with respect to each other, okay? So this is particularly strange. Both of these things are moving. The box is experiencing a kinetic friction from the desk and a static friction from the calculator. The calculator is only experiencing a static friction, nothing else. So this is when friction gets weird, because of situations like this, where it's moving, this calculator is moving, so students and people, not just students, everybody, wants to immediately think of kinetic friction because it's moving, but in fact the calculator is experiencing a static friction between itself and the box. Okay? So we use the symbol F again with a subscript K to designate kinetic friction. And it is a single value. It's easier to think about. It has nothing to do with the speed it's moving at or anything, right? It's some single value does not change speed or pushing force. So the static friction alters with the pushing force, the kinetic friction doesn't. So in a way it's easier to deal with because it's just a single value. Now it changes depending on the mass of the object and whether you're on ice or gravel, right? Obviously the value changes. But once you have a car with rubber tires on pavement, no matter how fast it's going, the friction is the same. The kinetic friction is the same. And the whole idea of it's harder to get it started than it is to keep it going. The kinetic friction is less than, for a given material, the kinetic friction is less than the maximum static friction. So it's harder to get it started, takes more, right? There's more friction that's involved before it starts to move. The instant it starts to move, that friction turns into kinetic, and that's actually less. So it's easier to move something along than it is to get it started. So I could have an example that say it takes 5 newtons to start a box moving, and newtons to keep the box moving at constant speed. How much force is required to accelerate it by 1 meter per second squared. So I'm giving you a bunch of different forces. I'm saying, okay, here I've got this thing. I'm pushing on it, I'm pushing on it, I'm pushing on it. It takes me 5 newtons to start it. Then it only takes me 4 newtons to keep it going at a constant speed. But now I want to accelerate it across the room. The friction doesn't change, we've said, but the pushing force does. To make it accelerate, I have to push harder than to keep it moving at a constant speed. So we have kind of 3 different scenarios. We've got the scenario where there's some push force of 5 newtons. And that occurs at the maximum static friction. And I know that because that's when it starts to move. That's why I know that that's the max static friction. But at this instant, it's net force of 0. It's not moving. A split second later, it starts to move. So at that point, I've got a 4 Newton force that's pushing it along. My net force is still 0 since there's no acceleration, but it is moving. That usually bothers people. The idea that you have a net force but it still moves. But it's that whole idea, right, of if it's not accelerating, F equals ma. If it's not accelerating, the net force has to be 0. So at this point it's moving, so there's a kinetic frictional force. My third scenario is I'm pushing with some other force that I don't know in such a manner that I make it accelerate at 1 meter per second squared. So I've got acceleration of 0. Acceleration of 0 because it's not moving. Acceleration of 0 because it's moving at constant speed, right? And acceleration of 1 because they told me so. There has to be another force, right? We know that this is a frictional situation. So there's this frictional force opposing this motion. So this is the problem we're asked to find. We're asked to find this pushing force that you push it in order to get this 1 meter per second squared. So I'm going to think about this in terms of just a basic force problem, like we did at the beginning of class. And I'm going to say, okay, in the x direction, the net force in the x is the mass times the x acceleration. I've got 2 forces, so my net force is comprised of 2 different forces, and I can write them out as negative Fk plus F push equals ma. Oh, I know my A. I need to know my mass too. This is what happens when I make a problem up. Let's say the mass is 2 kilograms. Okay? So I put 2 kilograms in here. So I know my frictional force points to the left, which is why it's negative. I know my push force points to the right, which is why it's positive. If I add those together, I have to get the mass times the acceleration because they're the only forces acting in the x direction. But I'm missing something because I need to solve for the push force. That's the goal of the problem. So I've got a push force is 2 newtons plus the static frictional force. Kinetic frictional force. Does everybody see what I did here? Okay. But this, I need to know this. And I don't know it. It wasn't given. But I have this second scenario over here that I drew a picture for and haven't really thought about that will actually help me solve for the kinetic friction. And these two kinetic frictions are the same. That kinetic frictional force doesn't change based on the speed you're moving or whatever. It doesn't matter. So I can use this situation to find my kinetic frictional force and then transfer it over to here. So let's look at this situation. I've got 4 newtons, kinetic friction, constant velocity, so acceleration is 0. You can make a conceptual argument that since the acceleration is 0, the forces have to be equal and opposite to get a net force of 0. Or you can go through and do the formal way. So it looks exactly like this. F net x equals max. I've got a negative friction, a positive 4 newtons, and that has to equal 0. So I've done the exact same thing I did here. And so obviously in the formal way we see that the kinetic frictional force equals 4 newtons. And now I can take this and plug it in there, because the kinetic friction doesn't change. So I end up with a push force equal to 6 newtons. So it required 5 newtons of pushing force to make the box move. It required 4 newtons of pushing force to keep it moving at constant speed. It required 6 newtons to accelerate it at 1 meter per second squared. If I want to accelerate it at 50 meters per second squared, I'd obviously have to push harder. But the frictional force, the static friction, is 0. 1, 2, 3, 4. Now kinetic takes over. It moves, right? Now I'm moving at constant speed with 5 newtons of force. Now I want to accelerate it, so I'm going to push harder. Okay? Okay. So, you guys get this kind of a little bit? Well, so it turns out that there's special equations for these forces. This is kind of the concept behind friction. It turns out there's special equations for these frictional forces as well. So, friction depends on what you're sliding across. If I'm sliding the book across the desk versus sliding it across an ice rink, clearly the friction is different. Ice is less friction than the desk is. It also turns out that heavier objects have a different type of friction. A bus trying to drive in snow has an easier time at it than a little car trying to drive in snow. The heavier bus actually has more friction for the same snow than the car does. Okay? So we need some equation to encompass all that. Okay, so this is the equation for kinetic friction. This is the kinetic frictional force. This is the normal force. How do you guys do normal force? With a capital N, or do you do F sub N?
Absolutely.
Okay. So you've learned about this force already. This is that force that's the contact force between surfaces, and it always points perpendicular to the surface, which is why it's called the normal force, because normal means perpendicular in math. This thing right here is called the coefficient of kinetic friction. So be careful when you do your homework problems. Sometimes they say kinetic friction force and give you a value. Sometimes they say coefficient of kinetic friction and give you a value. And I have students all the time that mix those up because they both are kinetic friction associated with kinetic friction. The main difference is that this is a force, so it has units of newtons, right? Normal force is a force, so it has units of newtons. So I got a newton on the left, a newton on the right. So the coefficient is unitless. It's the first thing you guys have seen that doesn't have a unit. This is actually so when you're reading the book and they just give you a value for something, you would know whether it was the coefficient or the force based on the unit. All right? This is material dependent. So like you have to, there's a table in your book on page 163. Table, page 163, that lists different coefficients of friction for different materials. So it's material specific. The coefficient of kinetic friction of ice is less than the coefficient of kinetic friction of gravel. Because it's a hell of a lot easier to push stuff across ice than it is to push it across gravel. And so there's a list in the book of all these different values, and it matters, it's not just the surface, but it matters what you're pushing across the surface. If I push an ice cube across ice, it's different than if I push a rubber block across ice. There's still ice, but it's ice on ice versus rubber on ice. So like if you look at this table, it talks about rubber on concrete, steel on steel, dry, steel on steel lubricated, wood on wood, wood on snow, ice on ice. It gives you all these different examples. One thing to note is that the coefficients of friction are always less than or equal to 1. So UK less than 1 always. It's equal to 1 with rubber on concrete, so I should put less than. If you end up and you're doing your problem and get a coefficient of friction of 3, you have done something terribly wrong. So with my students, if they circle the answer, coefficient of friction is 3, I take a whole lot more points off than if they have a wrong answer that is less than 1. So the normal force is based on the weight. It's not the weight, or it's not the, let me rephrase that. The normal force is not the force of gravity, always. Sometimes it is, sometimes it's not. Right now, this book is sitting on this desk. There's a normal force pushing up, gravitational force pushing down, and those are equal and opposite because the book is not moving. But if I grab a hold of this and lift it ever so slightly, right? It's not off the table, but I'm supporting some of the weight by doing this. So now the normal force is less than it was before. Still the same gravity, right? But I'm supporting it a little, so the normal force is a little less. Imagine somebody standing on your foot. Would you rather them stand on your foot without pushing up on a table, or would you rather them stand on your foot while they push up on the table, right? If they push up on the table while they're standing on your foot, it doesn't hurt as much because the normal force is smaller because they're supporting some of the weight on the table. So, but it is related to the mass somehow. So you have to be careful, right? That's what this normal force is in here for, is it's somehow related to the mass. So a heavier mass object like a bus has a bigger normal force, bigger friction. So it's material specific and it's related to the mass. Both of those things like we talked about a minute ago. The static frictional force has a very, very similar equation. And it is that the static frictional force is less than or equal to mu s Fn. So this is the coefficient of static friction, which has a different value than the coefficient of kinetic friction. This is where we get the different values for frictions. The less than or equal is still there because it still varies, but this implies that the maximum static friction is exactly equal to this. Have you guys seen this symbol before? Okay. This is a Greek letter, it's mu. Really good words with friends word. I use it all the time with friends word. But it's a Greek letter mu, it's a U with a front tail on it. Right? You can draw a U and you can put the front tail on it. Okay, so let's do some problems with this so that we can kind of see how to link all of this stuff together. Let's see what I got. So this is going to be, I'm going to do number 17 in your book. Says, Bonnie and Clyde are sliding a safe across the floor to their getaway car. The safe slides with a constant speed of Clyde pushes from behind with 385 newtons of force, while Bonnie pulls forward on a rope with 350 newtons of force. What is the safe's coefficient of kinetic friction on the bank floor? So you've got a box. You've got a pushing force, right? Clyde is pushing from behind. You've got a pulling force, because there's a rope attached to the front that's pulling it, so there's two people kind of motoring this box along. There's clearly kinetic friction, because we're dealing with real-world situations. Not that Bonnie fly is a very real-world situation. Okay, I guess it would. So we're dealing with kinetic friction. There is friction. And we know that there's gravity, and we know that there's a normal force. These other problems I've done have kind of ignored those two forces, but we have to think about them now because this force is linked to that force by that equation we just read out. So these two are linked together through an equation, so I have to think about the y direction along with the x direction. And they give us some of the values. They tell us that the push force is 385. They tell us that the pull force is 350. What else do they tell us? They tell us the mass is 300 kilograms. And they tell us that it's moving at a constant speed. It says, what is the safe's coefficient of kinetic friction on a bank floor when it's moving at a constant speed? So E is constant, and that's the same thing as saying the acceleration is 0, right? And the question is what is the coefficient of kinetic friction? That's the goal. So the hardest part of these problems is drawing the picture. That is honestly, it's the hardest part of the problems. And sometimes the picture is really easy to draw, and other times it's really, really hard to draw. But without the picture, you can't solve the problem. The picture is the whole base of the problem. And this one was not particularly difficult to draw, but you'll see in a minute that some of them are. So I'm going to think about Newton's second law. That F net is the mass times the acceleration. That's Newton's second law. And I'm going to think about it in both directions, the x direction and the y direction. So if I'm going to do that, I need to label my x direction and my y direction. My students don't label that, I take major points. I don't know what Dr. So I'm looking, the whole time I'm doing this, I'm looking at my picture. I'm not doing anything but looking at my picture. I look at my picture and I've got a plus 385 Newton force, a plus 350 Newton force, and a negative coefficient, or negative kinetic frictional force. And that has to equal the mass, which I know is 300 kilograms, times the x acceleration, which is 0. Because it's moving at constant speed. So lo and behold, I can find the kinetic frictional force, which is not what they asked for. They asked for the kinetic friction coefficient. So I'm going to leave this here, and I'm going to do my y equation.